Good evening, all of you. Is the audio and video clear to everyone? Please tell. Right? So, in the previous class, we discussed some concepts based on Euclidean rings. So, in today's session, we start the concept of polynomial rings. So, before going to start this one, anybody has any doubts on the previous class? Please tell. Any questions or any doubts for anybody? Right. Then, so in a short form, what is meant by a polynomial ring? Generally, let us write a polynomial first. Say f of x equal to 2x cube plus 4x square plus 1. So, from this very polynomial, what we can say about this? So, if we have considered this polynomial, what we can say about this? The variable or indeterminate is x, right? It has only one variable, or we call it as indeterminate with the highest degree 3. Since it is a cubic polynomial, it has the possibility of having 3 roots, right? Any other thing can we share on this? Any other thing can we share on this? So, let us talk about the coefficients here. So, what we can say about the coefficients here? These are integers, right? So, generally, while writing a polynomial, you can consider integers, rational numbers, real numbers, and also complex numbers. Accepted? So, what happens if you talk of polynomial rings? Whenever you consider a ring R, you fix any indeterminate variable, say x or y. Whatever the indeterminate you want to mention, that you can mention. You consider a sequence of values or set of values in the ring R. So technically speaking, I have randomly selected a set of values in the ring R. Those are nothing but A0, A1, A2, so on, AN. Now, using this indeterminate, we are framing a polynomial here like A0 plus A1x plus so on plus AN x power n. So we can write it using the summation notation that summation I is equal to 0 to n ai x power I. This thing. So this we call it as a polynomial over R. So whenever we mention the word over R, it means that whenever you consider a polynomial, the coefficients are precisely taken in a ring R. That's it. Okay? Are you clear now? So apart from taking any different set, we are taking the coefficients especially from a ring. So apart from writing this entire polynomial, we simply mention in the way that f is a polynomial given by a naught, a1, so on, an. It means that by default we will understand that the variable is x. The coefficients are these things starting from constant term to the highest degree value. That's it. So there are two representations for it. You can write like this, or in this manner also you can write. Please take a note of this, then inform. Are you clear? Now, when do we say that equal? Is it clear? Right. So, when do we say that two polynomials are equal? So, if I have said that f of x and g of x are two polynomials where the coefficients are taken over a ring R, we say that f of x equal to g of x if both have same degree and respective coefficients are equal. The coefficients of like terms are equal. Accepted? Now, since you are talking about a ring, we can consider any kind of polynomial where the coefficients are extracted from the ring. So, all these polynomials together, if you consider into a set, that will become a ring again. So, symbolically, we write it as R of x. So, here x is the indeterminate. We mention this with square brackets. It means that we are considering all possible polynomials where coefficients are taken from the ring R. So this will become a ring with respect to addition and multiplication of polynomials. So how to add two polynomials and how to multiply two polynomials, that we discuss later. So with respect to addition and multiplication of polynomials, we call it as a ring. Obviously, if you take the ring R, it always contains the zero polynomial 0. So in R of x, we write it as 0 plus 0 into x plus 0 into x square plus so on. This is the zero polynomial. Symbolically, we write it as 0 bar. And also, every element in R can be treated as a polynomial, just like constant polynomial. Suppose if you take the element 5 belongs to R, then what happens? This can be written as a polynomial like 5 plus 0 into x plus 0 into x square plus so on. So every element in R, we can treat it as a polynomial in R of x. And similarly, if you take the element 1 belongs to R, 1 is also a polynomial in R of x. The best advantage here is R of x is a ring. It is an integral domain, but it is not a field. So technically speaking, if you take R as a ring, R of x is corresponding polynomial ring. If you take D, the integral domain, as a ring, corresponding polynomial ring is D of x. Similarly, if you take the field F, corresponding polynomial ring is F of x. Are you clear? And one more thing is, while writing the polynomials here, we need to consider that whatever the ring you have chosen, while adding or multiplying the polynomials, same operations we are applying on the coefficients. That we need to understand. Okay? I think all of you know about how to add two polynomials. Is it necessary to take a problem on that? How to add two polynomials? Anybody? If I simply give two polynomials, right? Now let us discuss the concept that how to multiply two polynomials. That we discuss now. There is a small technique specified while multiplying the polynomials. I am just starting with a basic example. Suppose you take the polynomial f of x equal to 1 plus x, and another polynomial is g of x is equal to 3 minus 2x plus x square. Generally, while writing a polynomial, we take care that starting from the constant, we start writing it. So constant x, x square and so on, the highest leading coefficient, whatever it is that we consider. And here we are calculating f of x dot g of x, the product of the two polynomials. So while comparing the degree of these two polynomials, it has degree 2, it has degree 1. So for computational convenience, I am writing it as 0 into x square. Now, if you consider the product, apart from regular multiplication, the technique here is, you assume that this polynomial is of the form a0 plus a1x plus a2x square plus so on. Here also you assume that this polynomial is of the form b0 plus b1x plus b2x square plus so on. So while multiplying these two, we can obtain the value of f of x dot g of x. So we can easily verify that it also contains constant term, x, x square and other values also. Now the thing is how to find their coefficients. So if you multiply the constant terms together here, a0, b0, it is always the constant term in the product polynomial. So here we are going to multiply 1 into 3. So this is the value. Accepted? And if you want to find the coefficient of x, how to calculate that? Here the technique is, what is the power of x here? Its power is 1. So here we are multiplying some a values with some b values in such a way that the suffixes, if you add them, it must be equal to the power of x. So here you are taking x power as 1. So in these two things, we select those a values and b values such that if you add the suffixes, it must be equal to 1. So from that very observation, I can say that a0 b1 plus a1 b0 is the coefficient of x. How I have confirmed that? Here the power of x is 1. If you add the suffixes, 1 will come. So here a0 is equal to 1, a1 is equal to 1, a2 is equal to 0. From the second polynomial, b0 is equal to 3, b1 is equal to minus 2, b2 is equal to 1. So from this relation, can you tell the coefficient of x there? a0 b1 plus a1 b0. One. All of you agree? Any doubts for anybody? Right. So if you are calculating the coefficient of x square, how it comes? Since the power of x is 2, we will take those values that a0 b2 plus a1 b1 plus a2 b0. So you can observe that the sum of the suffixes equal to the power of the x. So from this relation, what is the value of coefficient of x square? I think it will be minus 1. So you can take the coefficient of x cube also. It is nothing but a0 into b3 plus a1 b2 plus a2 b1 plus a3 b0. Now you can tell its value. I think it will be 1 again. Accept it all. So the technique here is, basing on this procedure, you can write a computer algorithm so that whenever two polynomials are given to you, by simply reading the coefficients, we can calculate the product polynomial there. Okay? Right. Now the thing is, how many coefficients we need to calculate here? Any guesses from anybody? In other words, up to what power we have to consider this polynomial? Is there any relation for that? Three. Now, here we need to understand a small thing, that whenever two polynomials are given, if you are adding them, let me say the result is non-zero. In such cases, the degree of the polynomial will be maximum of degree of f of x comma degree of g of x. That means in the two polynomials what you have considered, which polynomial has the highest degree, that will be the degree if you calculate the addition. So it will be generally less than or equal to. It need not be equal to always, because while adding the coefficients, if the highest power coefficient becomes 0, you will get a less degree polynomial. So you can know the degree of f, degree of g, among which degree has, which polynomial has more degree. So if you consider the addition is less than or equal to maximum of the 2 degrees. So if you consider for the product, so degree of the product polynomial, degree of f into g is less than or equal to degree of f of x plus g of x, degree of g of x. So you consider degree of f, degree of g, you add them, you will get a new number. So degree of the product polynomial is less than or equal to that one. So here degree of f is 1, degree of g is 2. If you add, you will get 3. So here you need to calculate the coefficients up to x power 3 value. Okay. So x power 4 will not come there. Is it clear for all? And one interesting thing is the polynomials what you have taken, if they are taken from a field, then always degree of the product polynomial is equal to degree of f plus degree of g. Generally it is less than or equal to. If the polynomials are taken from a field, degree of the product polynomial is equal to degree of the first one plus degree of the second one. That is the maximum degree which we can get there. Are you clear? Any other questions for anybody? Please take a note of that. Shall I proceed? Okay. Now, consider the ring Z6 with respect to addition modulo 6 and multiplication modulo 6 operations. The corresponding polynomial ring here is nothing but Z6 of x. It means that you can consider any polynomial of any degree where the coefficients are nothing but 0 to 5 only. Other numbers will not come here. Such kind of polynomials we are taking care. Now what happens, I just want to take a small example that suppose you take the polynomial f of x is equal to 1, the constant polynomial, let me say, and you can take the other polynomial, say, or you can take f of x is equal to 1 plus x square. You take the constant polynomial 1 is equal to I of x, the identity polynomial. Now, here I need to calculate the product polynomial. Just give me a moment, I will write. So let me finish the writing first, then I will give the proper explanation on it. Now please take a note of this. Now I will explain what is the underlying idea here. So our intention here is whenever we consider a polynomial ring, the maximum properties that it will exhibit are it is a ring, it is a commutative ring, it will be an integral domain if you take the domain as a field. So it cannot be a field always. It is the maximum, you can say it is an integral domain. That's all. Now the best example for is you can consider the value Z6. It is a ring where the operations are taken as plus 6 and multiplication modulo 6. The corresponding polynomial ring is Z6 of x. So I am saying that it will become a commutative ring, it will has the unity element, but it is not a field. Why? Because suppose you consider a polynomial f of x is equal to 1 plus x square in this ring. And obviously the constant polynomial 1 is nothing but the identity polynomial. If you want to say that it is a field, we can say that every non-zero polynomial must has inverse in it. So suppose the inverse is existed there. Say g of x is the inverse of f of x here. Then what happens whenever you consider the product? F into g is nothing but identity polynomial 1. Now you consider degree for these two things on both sides. So the degree of constant polynomial is 0. On the left side you have degree of f into g is there. So from the very observation it is degree of f plus degree of g which is equal to 0. Since it is a non-constant polynomial or whatever the case may be, from the very thing degree of f of x is 2, whatever the value you can take here, you cannot get 0. Because degree of a polynomial is always a non-negative integer. So for a polynomial, the degree may be a positive value or 0. For constant polynomials, degree is 0. For non-constant polynomials, you can take 1, 2, 3, 4, so on as degree. And for 0 polynomial, degree is not defined. As and when you mention that g of x is inverse of f of x, it means that g of x has at least degree 0 or greater than or equal to 1. So while comparing the result, it has degree 2. Whatever the number you take here, you cannot get the output as 0. Therefore, g of x cannot be inverse of f of x. So every polynomial need not possess inverse in this set. Therefore, the maximum possibility for is it is just an integral domain but not a field. That we can take into consideration. So after noting, you please tell. So any queries for anybody on this? Any queries for anybody? All right. Now, how do we calculate the roots of the polynomials? And how do we perform division? Right? That we discuss now. Now see, suppose we have taken the polynomial x power 4 plus 4. And it is taken on the ring Z5 of x. Because Z5 is nothing but 0, 1, 2, 3, 4. And if you want to say what are the roots of this polynomial in the set Z5. So you simply substitute one after the other all these values here. So if you consider, say this is f of x, consider f of 0. This is 4, you are not getting 0. So if you have written f of 1, this is nothing but 1 power 4 plus 4 equal to 5, and this is equal to 0. In other words, 1 is root of this polynomial. Why? Because on Z5, the operations are addition modulo 5 and multiplication modulo 5. So whenever a number is equal to 5 or exceeds 5, you have to divide with 5 and you should take the remainder as the output. And if you consider f of 2, it is 2 power 4 plus 4 equal to 20. So under modulo 5, this is 0. Similarly, you can find the other roots. 3 is also a root because f of 3 is equal to 0 under the operation. And 4 is also a root because f of 4 equal to 0 here. Now, apart from this Z5, if you take the regular numbers, we cannot say that 1, 2, 3, 4 are roots of the polynomial f of x, because you will never get 0. You will get a positive integer as an output. But if the operation is changed, then these will become the roots of the polynomial f of x. And if you start writing factors, it is x minus 1 is a factor, x minus 2 is a factor, x minus 3 another factor, x minus 4 another factor. Multiplying all these values together, you will get f of x as well. So, if you consider the product of factors x minus 1, x minus 2, x minus 3 and x minus 4, here you will get a fourth degree polynomial, x power 4 plus some coefficient to x cube plus some coefficient x square plus some coefficient x plus 4. This thing you will get if you multiply all these values together, the factors. Now what happens? The coefficients here are nothing but multiples of 5. Since you are applying addition modulo 5 and multiplication modulo 5, so these values will become 0 there, right? You take a note of this. So any questions for anybody here? So similar the case we perform with division also, right? So whenever two polynomials are given to you, f of x and g of x, and you are dividing g of x with f of x, the division procedure is as usual, the regular way we perform the division. And while subtracting the coefficients or adding the coefficients, we follow the same technique here. Suppose if you are taking the group, the ring Z3 or Z5, so if you are dealing with Z3, whenever the coefficients exceed 3 or equal to 3, we have to take the respective remainder. Similarly, if you are performing the division over the ring Z5, then whenever the coefficients exceed 5 or equal to 5, we should take the remainder, right? That is the normal procedure while performing division as well as multiplication. And one interesting thing we can observe is, what will be the remainder when you divide a polynomial, especially with a linear polynomial. Let me say, I have taken a polynomial f of x, and I just want to know what is the remainder if I divide with x minus 3. Then what happens? Here 3 is the root, so you simply substitute the value 3 in place of x in the polynomial. whatever the number comes as output, that is the remainder. Okay, that you take a note of it. Even if it is noted, no problem. And after this, we discuss one interesting thing for the polynomial rings, that as we know, irreducible elements are there, prime elements are there in a ring. In polynomial rings also we have the irreducible polynomials. So what is meant by an irreducible polynomial? So it is nothing but, if you take a non-constant polynomial, say f of x belongs to r of x, then you cannot write it as product of two non-constant polynomials. So whenever this type of situation happen, it means that it is reducible. Let us take a simple thing, that suppose we have taken the polynomial x square minus 5x plus 6. We simply write this polynomial as x minus 2 into x minus 3. Accept it all? The polynomial, we can write it as product of two factors. Here what happens, degree of this polynomial is 1, degree of this polynomial is 1. So these two are nothing but non-constant polynomials. So we can say that this polynomial is reducible because it is possible to write as a product of factors. Irreducible means product of factors is not possible, right? Such polynomials we call it as irreducible. So whenever this type of situation is existed, we call it as reducible. Not existed, we call it as irreducible. In other way, if you are able to find root of a polynomial, then it is reducible if root existed. If no root existed, means it is irreducible, because as and when a single root you have calculated, then immediately you can write f of x is equal to product of two values. So it can be reducible. Clear? So while checking for the irreducibility criteria, there is one good result, that Einstein criterion. So what is meant by Einstein criterion? So this is a technique useful to verify whether a given polynomial is irreducible or not. Suppose I have taken the polynomial f of x is equal to a naught plus a1x plus a2x square plus so on plus an x power n belong to z of x. I want to know whether this polynomial is irreducible over Q. So over the rational numbers, I want to verify whether it is irreducible or not. So Einstein criterion says that if you are able to find at least one prime number p such that in the coefficients p divides the constant, p divides a1, p divides a2 and so on, p should not divide the leading coefficient, and p square should not divide the constant term. If you are able to find this type of prime number, at least one prime number is existed with this property, then the polynomial what we have taken is irreducible over Q. If there is no such polynomial, we say that it is reducible over Q. Okay? So please take a note of this condition. After noting, please inform. Now, if you take a sample example that, say, I have taken the polynomial f of x is equal to x power 4 plus 2x plus 2. Let me say, I have taken the polynomial in such a manner. Now, if you write in the specific notation of a polynomial, we should write it as 2 plus 2x plus 0 into x square plus 0 into x cube plus 1 into x power 4. This is the standard notation of the polynomial f of x. Accepted? Now, the prime number, what I can decide here is, I will take the prime number p is equal to 2. So here, p divides the constant term, p divides the coefficient of x square, coefficient of x cube, and p is not dividing the leading coefficient, and p square is not dividing the constant term. Accepted? Since I found a prime number p from Einstein criteria, this polynomial is irreducible over rational numbers. That was the conclusion. So here we need to understand one more thing, that Einstein criteria always gives 99% results, but it is a necessary condition but not sufficient. It means that there are some polynomials, even though Einstein criteria is not satisfied, they are irreducible. Okay? Yes? Square is not divided 2 because p square is 4, 4 is not dividing 2, the constant term. This is the condition. The prime number p is dividing every coefficient except the leading coefficient. The square of the prime number is not dividing the constant term. That was the condition. Here, what is the constant term? This is 2, right? The prime number is 2. Is 2 square dividing 2? Is that right? That's why 4 will not divide 2. So let me take one more example, then you have the idea of this Einstein criteria. Suppose I have taken the polynomial x power 5 minus 9x plus 3x square minus 12. So this thing you can say in a formal way, you can write it as minus 12 plus 0 into x plus 3 into x square plus 0 into x cube minus 9 into x power 4 plus 25x power 5. Now if the question comes that is it reducible or irreducible, here we say that you take the prime number p is equal to 3. So 3 divides minus 12, 0, 3, 0, minus 9, and 3 is not dividing 25. And if you consider p square, this is equal to 9. This does not divide minus 12. Okay. Is it clear for you? It is an irreducible polynomial over Q. Now, is this example gives sufficient knowledge to you with regard to the irreducibility? Understand one more thing, that this technique is useful to verify irreducibility over rational numbers only. We are not checking the irreducibility over real numbers as well as complex numbers. Please understand that. We are not checking the irreducibility on real numbers as well as complex numbers. So always understand one thing, that if I have taken a polynomial, reducibility of the polynomial means whatever the ring you have considered, on that ring it must be factorized. That means factors are existing in the ring. Irreducibility means you cannot find factors in that ring. That is the whole idea. Now, let's take one simple example that will give an idea for you. Suppose take the polynomial x square plus 1. So this is nothing but x plus I into x minus I. Accepted? The polynomial. Now what happens? Is it reducible or irreducible? Is it reducible or irreducible? Please specify. Right? It is reducible because we have calculated the factors. Now understand one thing, that from the very factors, if you observe the coefficients belong to the complex number system. Accepted? In other words, I is a root and minus I is a root for the polynomial. What you have taken? So we say that this polynomial is reducible over the complex number system, and it is irreducible over real number system. You please take a note of this. So reducibility or irreducibility is totally based on the rings what you have taken. Is totally based on the rings what you have taken. Okay. So the other important thing here is, even though it is factorized, we observe that the polynomials in the factorization belong to which set? So if they belong to the complex number system, it is reducible over the complex number system and irreducible over the others. That is the fundamental thing. So the same polynomial is becoming irreducible over R and it is becoming reducible over C. So while checking the reducibility or irreducibility, the ring is very important. On what set you are checking the roots. So Einstein criteria is useful to check for the irreducibility over rational numbers only. I have taken a polynomial whose coefficients are integers. So that integer coefficient polynomial is irreducible or not on the rational number system, I am checking by means of Einstein criteria. Okay? Does it make sense? I took a polynomial whose coefficients are integers. So if you take a polynomial whose coefficients are rational numbers or something, then we cannot apply Einstein criteria there. Einstein criteria is applicable only the irreducibility over rational numbers for a polynomial whose coefficients are integers. Clear now? And I will say that you can occasionally find some polynomials where Einstein criteria is not applicable, but it is irreducible over Q. I will give an example as a posters in Telegram group later. You can check that. It's a small problem that you can cross verify. Why we are giving maximum stress on the concept of irreducible? Because for every ring you can calculate the ideals. So in a polynomial ring also we can calculate the ideals. So what is the ideal structure there? So it is a multiple of a polynomial. Generally the multiples of x, the polynomial x, so the general structure is x into f of x, the multiples of. So whatever the polynomial f of x you consider, x into f of x multiples is nothing but an ideal in the polynomial ring. Now what happens if you take a f of x which is irreducible polynomial, then this will become the maximal ideal. So if you take that f of x is an irreducible polynomial and you consider all the multiples of f of x, so all these multiples together constitute an ideal and that ideal will become the maximal ideal. Okay, and we have one famous result that R by I is a field if and only if I is maximal. Similarly, R of x by generated by f of x is a field. So if and only if f of x is irreducible. That is the advantage of it. Now I will give a simple technique that suppose you have taken the polynomial ring Q of x by the polynomial multiples x square minus 5x plus 6. Now the question is it a field or not? So for that, it is enough. We have to verify whether the denominator polynomial is irreducible or not. Because if it is irreducible, this polynomial multiples will become maximal ideal. If it is maximal ideal, the quotient ring will become the field as per the known results for us. So, is this polynomial x square minus 5x plus 6 irreducible or not? It is not irreducible because we can make it as factors. And these factors belong to Q of x also. So it is a reducible polynomial. Hence, this is not a field because the polynomial has become reducible. So it is just a quotient ring, but it is not a field because the denominator is not a maximal ideal. Okay? There is a proof. An ideal is maximal if and only if it is generated by irreducible polynomial that we discuss in the next class. The result part. Irreducible polynomial multiples always generate the maximal ideal. Right. And always f of x is a principal ideal ring. So if you take a field f of x is nothing but set of all polynomials with coefficients are taken in the field, and this polynomial ring is always a principal ideal domain. So whatever the ideal you consider, it is multiple of some polynomial. So these results we will discuss in the next class. I am just giving the outline for them. So I want to mention one more thing, that this is also a previous year question. Let us discuss that now. Then we can wind up our today's session. So in tomorrow's class, we will take more number of problems on the results based polynomial rings. So the result is, if you want to say f of x is irreducible, you can verify with f of x plus 1. That means in place of x, you replace with x plus 1. Not only x plus 1, you can take x plus 2, x plus 3, x plus 4, any integer. So if you want to check whether a given polynomial f of x is irreducible, it is equivalent to verify that f of x plus 1 is irreducible or not, if you don't have any straightaway method for the verification of f of x. Clear? This is one good result. Based on this, a problem is given in the UPSC. You take a note of the result, then we start the problem. After noting, please tell. So the question is, we are going to verify that this is the polynomial I have taken where p is a prime number. P is any prime. Whenever you consider a polynomial of this form, it is always irreducible over the rational numbers q. Here also we apply the Einstein criterion. So for a general visualization, suppose I have taken that p is equal to 5. So what is my intention here? I am going to verify that. So 1 plus x square plus x cube plus x power 4 is irreducible over q. If I have taken that p is equal to 11, then what will be my polynomial? 1 plus x plus so on plus x power 10 is irreducible over q. That is the strategy of the problem. Okay? Is that fine? Now, let us consider the given polynomial where p is a prime number. This is my given polynomial. I will give the name as f of x. Say this is equal to f of x. Now, I can write this polynomial as because you can visualize this. This is nothing but sum of the terms which are in GP, the geometric progression. Sum of the n terms in GP, the geometric progression. Here the common ratio is x. Accepted? So sum of the terms in GP using the formula, this is my result. As you have a formula, a into r power n minus 1 by r minus 1. Can you recollect this? Sum of the n terms in geometric progression, where r is the common ratio. So applying this, that will come. the given polynomial. You can cross verify that. And one more thing is, my intention is that I have to show this is irreducible. This value is equivalent to this. So I have to prove that this is irreducible. Since there is no technique available to me straight away, apart from taking f of x, I can consider f of x plus 1 because these two results are equivalent. So I will consider f of x plus 1. So this is nothing but x plus 1 whole power p minus 1 by x plus 1 minus 1. These two things gets cancelled. So writing this by using the binomial theorem, this is nothing but x power p plus pc1 into x power p minus 1 plus pc2 into x power p minus 2 plus so on plus, so pcp minus 1 whole by x. So do you accept that? Now what happens? PCP is nothing but 1. So these two gets cancelled. So dividing this whole thing with x, the result is x power p minus 1 plus pc1 into x power p minus 2 plus so on plus pcp minus 1 into 1. I have divided each and every term with x. Now what happens? Here p is a prime number. So for example, if you elaborate this polynomial, for example, say p is equal to 7. What is this? This is nothing but x power 6 plus 7c1 into x power 5 plus 7c2 x power 4, 7c3 x cube, 7c4 x square, 7c5 x, 7c6. Am I correct? If you take an example, now you can observe that all these values 7c1, 7c2, 7c3, all these values are nothing but multiples of 7. You know the formula, NCR formula, right? That you can cross verify by means of Pascal's triangle also. Because the binomial coefficients will come under the Pascal triangle. Suppose randomly check, I think you know how to construct Pascal's triangle. So if you are interested, let us write that. So this is the Pascal's triangle. So 7c0, 7c1, 7c2, 7c3, 7c4, 7c5, 7c6, 7c7. Accepted? The binomial coefficients there under the Pascal's triangle. I think this thing you know how to construct the Pascal's triangle. See? So from this, all these values are nothing but the multiples of 7. The prime number what you have taken. So here p is the prime number, whatever the prime you have started in the problem. So it divides 7c5, 7c6, 7c4, 7c3, 7c2, 7c1. All these coefficients are divisible by 7. And leading coefficient is not divisible by 7. 7 square is not dividing this thing. So in the given problem, whatever the value of p is given, the same p satisfies the identity criterion here. Therefore, by definition, f of x plus 1 is irreducible. Hence, equivalently, given polynomial f of x is also irreducible. That was the idea behind it. So f of x is irreducible. We have verified by applying Einstein criteria for f of x plus 1. Okay? Please take a note of that. So at this point, I want to conclude my today's session. Tomorrow we will take more results based on the polynomial rings.